Good evening, all. It's an immense pleasure for us to meet you in the virtual event and present our topic on reviving QEMU-NVMe device and its journey towards a subsystem. Myself, Karthik Balan, joined with my colleague Golu Appala Naidu, we represent from Samsung Electronics and we primarily work on the NVMe SSD group, which is responsible for the qualification of the NVMe devices. Now, we like to highlight on the disclaimer part for your observation. Today we will touch upon the below topics. So outline of this session is like reviving QEMU-NVMe device. We'll touch upon the introduction and revision histories, and we'll move to the QEMU-NVMe subsystem, followed by NVMe namespace, metadata use cases, which includes a format NVMe and production information enablement, and additional features from Samsung open source repository like usage and the features of it. And finally, we end with a small demo and the conclusion part. So let's start with reviving QEMU-NVMe devices. So before we start, what is a QEMU-NVMe? So let us have a small introduction on that. QEMU is a generic machine emulator and a virtualizer. It supports multiple architectures and it has a huge collection of emulated devices. NVMe is one part of it, and it is a very much an active community, and has around 130 subsystem maintainers, and then there are 1100 plus individual contributors like you and me who is working towards the contributions on it. Reviving QEMU-NVMe device. So going back to the history, in 2013 the initial commitment for the storage interface was started, where we had a basic PRP, read write, IOQ management, and identify and few circuit features. And after a long haul of 4 years, around 2017, the new feature write zeros were added. Again, NVMe 1.2 spec and controller memory buffer details were added in that. Later then, in 2019, there was a timestamp feature which is getting added to the QEMU, and in 2020 we had a persistent memory range. As of May 2020, the QEMU was becoming as a Franklin state. So it had a controller reported version as version 1.2, timestamp was from 1.3, and PM was from 1.4. At the end user, they were not sure what is the actual support from the QEMU. Then the things got changed from the September 20 patch, which was a bomb for version 1.3. The lot of refactoring, small fixes and cleanups were done, and fully functional 1.3 support were added, like commands like abort, get log page, asynchronous event, everything was added. And the NVMe QEMU device became like a 1.3 feature supported QEMU version for usage. In October 2020, the key part, SGL and multi namespace were getting added in this QEMU. Continued in 2021, the new commands in Feb we had added for dataset management, compare commands, and CMB, and we had attractions for 1.4 enhancements, and then the device was converted into version 1.4 spec compliance device, and the new industry trend zone namespace was added, and Samsung is happy to be a partner of this development in QEMU. In March 2021, the NVMe subsystem support was added, like namespace sharing, multipath IO, metadata support, and the new features like format NVMe, simple copy, verify, and the more key part of data integration, end-to-end data protection was also added in the QEMU device. Going next, my colleague Golu Appala will take you to the information on QEMU-NVMe subsystem.
Thank you, Karthik. Now we'll go through the NVMe subsystem architecture. So this is the basic solid state drive architecture. In general, in any solid state drive, there will be a bunch of NAND flash packages which will be controlled by the NAND controller, and we will have the PCI Express controller, and which will be like attached to the PCIe root complex. And since the NVMe is a PCI device, so it will be attached to the PCIe root complex, and the central to the device is the NVMe Express controller. So the same logic which is implemented by the QEMU device. So the QEMU emulated device assumes the presence of a flash translation layer, the FTL, by directly utilizing the logically addressable block layer. What does it mean? Like the basically the KMU device does not worry about the NAND, the backend NAND. So there is no FTL layer in the KMU NVMe. All we have is a KMU block layer to do the all the IO operations like writing, reading, deallocation, flush, and all these things, all these operations here, the L2B mapping, all these things are taken care by the logically addressable KMU's block layer. With this support, we are able to do this all the IO operations. Basically, the KMU architecture is like it is completely single threaded. When I say single threaded, the virtual CPUs which runs on a dedicated threads, but the simulated code, whatever emulation, that code we are running, right, it completely runs on the main thread. So if you use the blocked calls, the complete thread will be blocked. So but to in order to achieve the parallelism asynchronism, we use callbacks and expired timers in the KMU. So the device code, whatever the emulated code that we are implementing, that will be response to the callbacks and expired timers. With the help of these callbacks, we are achieving the asynchronous. So still the IO operations will happen asynchronously. These callbacks will be completed at some point of time, and the response will be given to the host and will trigger the interrupt. So the KEMU, currently the current master release is like 6.0.0. So at this place it supports a lot of features, like it supports complete NVM subsystem and namespace sharing and multipath IO. These things will, in the further slides we'll discuss more about these things. And the NVMe subsystem is modeled like a KEMU bus device, which is named as like a NVMe Subsys. And in this currently we are emulate up to 32 controllers. So each controller is again a KEMU generic bus device, and which is named as a NVMe device. It's a controller device, and we can emulate up to 256 namespaces. Each namespace is again individually configured, and which is modeled again, it's like a NVMe NS device. So as we could see here, the NVMe subsystem architecture. So whatever I told that in the previous slide, it supports so and so features. So I took a small NVMe subsystem model which is containing one subsystem, two controllers, and three namespaces. And we could see that the subsystem device is like NVMe Subsys, and the options we will give is like NVMe Subsys and Subsys equal to that subsystem ID. Apart from this, it has one more CLI parameter, that is NQN, the NVMe qualified name. By default we can use the name which is already present, or else if you wanted to change it, still we can change it from here. And the next level to the subsystem is controller devices. Here we could see that there are two controller device 1 and controller device 2. These are modeled as a NVMe bus devices. The naming is they named NVMe. So here we can see that the device is NVMe and its bus ID is NVMe 0, and it has some serial number we are giving. Apart from that, there are a lot of other parameters which are related to the any NVMe controller. So similarly for the second controller also, the ID is NVMe 1 and it has serial number, and again it can have a lot of other parameters also. So the next level to the controllers are namespace devices. So as we could see here, currently I have taken example of total 3 namespaces. So the first namespace is NVM. Again, the second one is also NVM. These are like conventional namespaces. These are like a normal namespaces. And the third one is a zoned namespace. I will showcase the parameter what we have to change in order to emulate the zoned namespace. And these namespaces devices are modeled as a NVMe NS bus device, and these namespaces device either private to the particular controller, or they can share the controllers among, or else they can be shared among the controllers in the subsystem. So as we could see here that, so the first namespace is only attached to the controller 1, which is private to the controller 1, and the second namespace, which is only attached sorry, the third namespace which is only attached to the controller device 2. So this is private to the controller 2, but the second namespace which is shared between both the controllers. Okay, so this is where the multipath IO from any of the controllers can do the IO operations on this particular namespace. And these namespaces can have their own uh, what we call like block sizes, block data structures, and other also metadata sizes. So the LBDS for this namespace is 9, and it does not have any metadata at this point of time. So LBDS 9 means it's a 512 block size namespace, and this one is, it has 512 block size, and also metadata size is 8 bytes, and this does not have any metadata, and it has a 512 block data size. So let's see how we can give these parameters while emulating the by emulating in the NVMe, QEMU-NVMe. So here we can see that the device is NVMe NS, and the bus here what we are mentioning is the controller bus ID. So we are mentioning here NVMe 0. So when you mention the bus is NVMe 0, the first namespace will be attached to the controller 1, and the ID is NVMe01, and this particular namespace internal ID, again the bus ID is NVMe0 at 1, and the drive is NVMe0 and 1. This is the backend namespace device, and this namespace ID is 1. And for the second namespace we are mentioning that the bus is the controller bus is NVMe1, so this will be attached to controller 1 if we are not mentioning shared option equal to true. If the shared option is equal to false, by default the shared option is false, that means then it will be only attached to the controller 2. But in this one we have mentioned that shared equal to true, that means this particular namespace will be attached to the both the controllers. Okay, and then again the same options, this particular NVMe NS bus ID and the drive backend NVMe image, and its namespace ID is 2, and it has a metadata size equal to 8. The third namespace similarly, and here the controller bus ID is NVMe1, so this will be attached to the second controller, and the NVMe NS bus ID and the drive ID, and its namespace ID is 3. And here we can see that we have mentioned it is like a zoned equal to true, that means this will be emulated as a zoned namespace device, and all the IO operations on this particular namespace devices will happen through the QEMU block layers. Okay, this is what we have discussed. Yeah, so this is pretty much about the QEMU-NVMe architecture. So we can see all these details in the as part of the usage. So this is what the meaning of each and every parameter that we give while emulating this QEMU-NVMe device. So the special thing is like here the namespaces, we are able to emulate the controllers, but here the thing is the namespaces which are attaching to the controllers in a shareable manner or in a private manner, that whole thing is getting managed, the everything that complete implementation behind the NVMe namespaces. The current QEMU NVMe devices supports like a multiple namespaces. So as I already told, these are designed through the NVMe QEMU devices. So the each namespace is individually configured. They can have their own metadata sizes, their own block data sizes, their own DL feed values, their own NS feed values, their own data production capabilities. Like it is uniquely configured. So they are individual and unique, each namespace. And we can support like we are also supporting that namespace attachment and detachment. We can at any point of time we can detach any controller from the any namespace from the controller, or we can attach any namespace to the controller, since we are already supporting the namespace attachment command. And during the boot up also we are attaching to the multiple controllers in a shareable manner. So the namespaces sharing across the controllers in the subsystem, as I have already discussed. So the namespaces are being sharing among the controllers within the subsystem. So, and it also supports the multipath IO. From if the namespace is shared between the two controllers, from any controller we can send the IO operations. And also the another beautiful feature that current NVMe namespaces have is like metadata handling. It also when it comes to metadata, there are like the T10 specifies mainly two types of metadatas. Like one is data integrity field format, that is diff, and another one is data integrity extension format. Both the formats current QEMU-NVMe device is supporting. So now we will see the namespace metadata, the use cases. I told that we are supporting the metadata, both the formats like both diff and dix, both we are supporting. But what is the use case? What we have achieved after enabling the metadata in the QEMU NVMe device? That I'm going to discuss in further slides. As we all know, the most common use case of the metadata is end-to-end data protection information. So from application to device, from device to application, will transfer some bytes of protection information, okay, through which we can enable the data protection. Okay, yeah. So by after adding support for the metadata, we are enabled features support for the format NVMe command. So this will format the NVMe namespace with the given namespace settings for and the next one, end-to-end data protection feature. So all the NVM commands like write, read, write zeros, verify command, copy command, all these commands have specified that how they will support the end-to-end data protection. That implementation also we have done after enabling the metadata in the QEMU-NVMe device. So as I told that metadata is in two different formats. First one is diff, data integrity field format, that is metadata in a extended logical buffer format. So what happens in this case is the PI information, the metadata will be continuous with the logical block data. So as we could see in this particular figure, this is taken from the NVMe specification. So there is a logical block data followed by metadata, again logical block data and followed by metadata. So this is basically the metadata settings. As per the NVMe specification, the MSET value is 1. So here in this one we'll use only data pointer, both based on the data size. We'll use both PRP1 and PRP2. Here we will not use the metadata pointer. So from either host to device or device to host. So this is how in a pictorial representation of the metadata in a diff format. So in QEMU, how we are handling this part? So in QEMU, what we are doing, let's say for example we have a 1 GB of uh, drive. So the first part will be for the data. The next we are having the for the data the drive, we are using it for the metadata. So in logical figure it looks like all the metadata is end of the data and metadata. This is how we have separated in the QEMU architecture. So but whenever there is a write operation, host will send logical block data, metadata, logical block data, metadata. So what we are doing here, we are splitting that metadata, we are and merging into one buffer, and we are writing at the end of the data. And at the time of reading, host reading the data, again we are reading and we are again merging. We are keeping the metadata, their respective metadata blocks after the logical block data, metadata, logical block data, metadata, and we are giving it to the host. This is how in QEMU we are maintaining this one. So yeah, here we could see that this is the data integrity extension format. So here that metadata will be transferred in a separate buffer. The metadata setting value is here 0. In this one, we will use both the fields, both metadata pointer and data pointer. So this is the exactly one the way we are using in the KMU. So as we could see here that the data logical block data is continuous. There is metadata is in a separate buffer. So LBN data, LBA n plus 1 data, and so on. So this is how in the KMU also we are storing at the end of this logical block data. Once all the logical block data is done, at the end of that we are storing the metadata. And in case of diff format, what we are doing is we are splitting and merging the metadata. So in case of DIX format, as it is, we are using over the NVMe namespace device. So as I have told that the format command has been enabled. With this, we are able to change the runtime namespace setting for like logical block format. So as we all know that the NVMe devices supports around 16 logical block formats from 0 to 15. So we can give like certain logical block data size bytes like 512. Generally usage is like 512 1024 4096 bytes. This is like a usual data block sizes, and metadata sizes are ranging from minimum of 8 bytes, because the protection information is minimum of 8 bytes. From there it depends, like 8 or 16 or 64 are generally used metadata sizes. So these we can configure. And also the metadata settings, like either we can format it with a metadata in a separate buffer, or else it's an extended logical block data format. And also production information types. NVMe devices supports total 3 types of production information: type 1, type 2, and type 3. So what should happen, what fields should be verified in each type of production information is also already specified in the NVMe specification. So we can change this data production information settings also. And also production information location, either it will be first 8 bytes or last 8 bytes, the production information, that also we can change during the runtime. So basically what can happen is, in a single device we can run it for the multiple configurations. Okay. And the data production, end-to-end data production, EDP. This feature basically like the data production between application and NVM data. Why I said like from application is the host side application will be there, that will send the production information. That will be sometimes the device will verify, or else sometimes the host will verify based on the settings we have enabled, based on the production information action field, pract field. Okay. At this present, like the QEMU-NVMe device supports 8 bytes of production information. The 8 bytes are like a God field, that's a CRC16, and then the application tag, it's a 2 bytes, and the reference tag, it is 4 bytes. And it has a data production capabilities like all the 3 types it will support currently, both 1, 2, 3. And the end-to-end data production feature is enabled for the all the NVM commands like write, read, compare, write zeros, copy, and verify commands. All the NVM commands which are enabled for the EDP.
Thank you, Apala. Let me quickly touch upon the additional features supported from the Samsung open source repo. QEMU-NVMe compliance. The Samsung QEMU-NVMe compliance open source repo contains some additional features which we'll be discussing later part of this slide, which will help you in the NVMe compliance program validations. These patches can be applied to the specific version of QEMU, and it is licensed under the general public license version 2.2 or later, and there is no issues from the licensing perspective for it. And Samsung is open for the contributions on this repo too from any of the interested persons in the global community. So what are the features which are there in this repos, especially are the boot partition, where you have a firmware download and firmware commit, and boot partition reads. And we also support boot partition Q test, and the features like write uncorrectable commands and device self-test are all supported in this version of repo. How the user can use this version? So currently it is built over the version of QEMU version 6.0. The user will be able to apply the patches to the later versions or the master directly, and the patches are managed by Quilt. The Quilt kept Vapor scripts only set up required environment variables, no other changes further. So we have given the repo link, which is basically Samsung's OpenMPDK repo, where you can find this version. Now let us come to the conclusion of this presentation. We understood that latest QEMU-NVMe device has a complete feature set, from a single controller to a subsystem with complete feature support. QEMU emulator device enables system technologies to left shift their design. They also help in easy prototyping of the next gen or experimental features. QEMU is an entire stock case model, not just their interface. It helps in faster ecosystem adaptation to the market. So we have added some of the references from where we have taken the images and stuffs. And once all, thank you for your time, and any questions please reach us to Golu Apollanaidu or Karthik Balan mentioned in the mail IDs. Please take a moment to rate this session. Thank you.